September 10, 2008, as the newest addition to CERN's complex of accelerators. The LHC is a massive 27-kilometer loop beneath the France-Switzerland border near Geneva, filled with superconducting magnets and other devices designed to increase the energy of particles as they move through the tunnel. The tunnel is so enormous that workers use bicycles to get around inside it. Inside this colossal machine, two beams of particles are accelerated to nearly the speed of light, traveling in opposite directions. These beams are contained within separate vacuum tubes and are guided along their paths by a strong magnetic field created by superconducting electromagnets. These magnets, made from special coils of electric cable, allow electricity to flow without any resistance, ensuring no energy is lost. However, to work properly, the magnets must be kept at an incredibly cold temperature of -271.5 degrees Celsius, which is even colder than space. To achieve this, the LHC uses a network of liquid helium to keep the magnets chilled and the system running effectively. Thousands of magnets of various types and sizes are used to steer the beams around the accelerator. This includes 1,232 dipole magnets, each 15 meters long, which bend the beams, and 392 quadrupole magnets, between 5 and 7 meters in length, which help focus the beams just before they collide. Another set of magnets compresses the particles, increasing the likelihood of collisions. The particles are so tiny that making them collide is like trying to shoot two needles 10 kilometers apart and having them meet precisely in the middle. The entire operation of the accelerator, including its systems and infrastructure, is managed by the CERN Control Center. From this single location, the beams within the LHC are controlled to collide at 4 points around the accelerator ring, where 4 particle detectors, ATLAS, CMS, ALICE, and LHCb, are positioned. For a long time, we understood the basic elements of nature like helium, hydrogen, oxygen, gold, and lead as made up of various types of atoms. A significant breakthrough came when scientists discovered that all atoms are composed of just 3 fundamental particles: protons, neutrons, and electrons. By adding more protons and electrons, we can create different elements and types of atoms. This means that theoretically, we could build a simple universe using only these 3 particles. However, in the early 20th century, things became much more complicated. Scientists began finding many new particles from cosmic rays, and there was no system in place to categorize them. They used names like pi, sigma, and delta, but the naming system quickly became overwhelming, and they ran out of symbols. To make sense of this chaos, scientists started organizing these particles based on their properties, such as spin, electric charge, mass, and how long they last before decaying. To simplify the picture, they predicted the existence of new fundamental particles called quarks. These quarks combined in different ways could explain all the observed particles, leading to the creation of the Standard Model. Initially, only 3 quarks were known, but as research progressed, a 4th, 5th, and 6th quark were discovered, which supported the model. Alongside quarks, there are leptons, fundamental particles that include the electron and its heavier relatives, the muon and tau, as well as their neutrino partners. The Standard Model also describes the fundamental forces of nature. The weak force, which governs processes like radioactive decay and energy production in the Sun, is carried by W and Z bosons. The electromagnetic force, responsible for light and magnetic interactions, is carried by photons. The strong force, which holds quarks together in protons and neutrons, is carried by gluons, which effectively glue the quarks together. While the Standard Model has been incredibly successful in predicting microscopic phenomena, it wasn't complete. The missing piece was the Higgs boson, often seen as the ultimate goal in particle physics. The Higgs boson is like a special key to understanding how other tiny particles get their weight. It's connected to something called the Higgs field, which acts like a magical force field that gives weight to particles like electrons and quarks. This weight, or mass, is what makes particles resist changes in their speed or position when they're pushed or pulled by a force. However, not all tiny particles have this weight. For example, photons, which are the particles that carry light and electromagnetic force, don't have any weight at all. Scientists had predicted the existence of the Higgs boson for over 40 years and used it in their calculations, but it remained undetected. To create a Higgs boson, particles need to collide with extremely high energy. However, for a long time, physicists were like explorers in the dark, searching without knowing exactly how much energy was required to make this happen. They knew they needed a specific energy level but had no idea what that range was, making their quest all the more challenging and mysterious. The Large Electron-Positron Collider, LEP, located at CERN in Europe, operated from 1989 to 2000. This accelerator collided electrons and positrons, and its collision energy increased progressively from 91.2 gigaelectron-volts to 208 gigaelectron-volts. LEP scientists aimed to create Higgs bosons by raising the beam energy to conditions conducive for their production. Despite their efforts, LEP was unable to detect the Higgs boson, but it did manage to exclude the possibility of a Higgs boson with a mass below 114.4 gigaelectron-volts. This exclusion was a significant step in narrowing down the particle's possible mass range. Following LEP, the Tevatron at Fermilab took on the challenge. From 1986 to 2011, this accelerator collided protons and antiprotons with collision energies ranging from 1,800 gigaelectron-volts to 1,960 gigaelectron-volts. The Tevatron could produce Higgs bosons, particularly for masses under 160 gigaelectron-volts, which would decay into bottom quark pairs. For higher masses, the Higgs bosons would decay into pairs of W bosons. However, the common occurrence of bottom quark pairs from other processes made it difficult to detect potential Higgs signals. Researchers focused on collisions where Higgs bosons were produced alongside W or Z bosons to improve detection. Despite these efforts, the Tevatron could not definitively detect the Higgs boson due to limitations in data and energy. The Large Hadron Collider, LHC, also at CERN, continues to play a crucial role in particle physics. After it began operations, the LHC collided protons with collision energies increasing from 7,000 gigaelectron-volts in 2010 to 13,600 gigaelectron-volts as of 2022. The higher energy and advanced detectors at the LHC allowed for the creation and study of Higgs bosons more effectively. The LHC's superior capabilities enabled scientists to observe rare decay modes, such as Higgs bosons decaying into pairs of Z bosons or photons. These rare decays provided clear signals for detecting the Higgs boson, which was challenging with earlier accelerators. On July 4, 2012, the LHC experiments ATLAS and CMS announced the discovery of a new particle consistent with the Higgs boson, marking a significant milestone in particle physics. This discovery confirmed the particle's existence, but further data was needed to verify that it was indeed the Higgs boson. Scientists conducted additional crosschecks, including verifying decay patterns predicted by Higgs theory. The extensive data collection and analysis confirmed that the discovered particle matched the predicted characteristics of the Higgs boson. The discovery of the Higgs boson was the result of decades of research and technological advancements. Each era of accelerators, LEP, Tevatron, and LHC, contributed critical insights and advancements that culminated in this groundbreaking discovery. On October 8, 2013, François Englert and Peter Higgs were honored with the Nobel Prize in Physics for their groundbreaking theoretical work on understanding how particles acquire mass. Their theories predicted the existence of a crucial particle that was later confirmed by the ATLAS and CMS experiments at CERN's Large Hadron Collider. Right after the Higgs boson was discovered, physicists eagerly began investigating its properties to determine whether it was the Higgs boson predicted by the Standard Model or something entirely different. The first step was to measure its mass, which had been the last missing piece in the Standard Model puzzle. They found it to be around 125 gigaelectron-volts, which is about 130 times heavier than a proton. This mass meant the Higgs boson could decay into various particles in different ways. The discovery of the Higgs boson marked the beginning of an exciting new chapter in particle physics. Scientists focused on understanding this unique particle, which stands out in the Standard Model for its lack of spin, electric charge, and strong force interactions. To confirm these features, they measured the spin and parity by analyzing how the Higgs boson decayed into other particles. The results matched the predictions, solidifying its identity as the Higgs boson. However, it's still unclear whether this is the only Higgs boson or just one among many, as some theories, like supersymmetry, suggest the existence of additional Higgs particles. While some of these theories have been disproven, others still need more data for exploration. By closely examining how the Higgs boson is produced and how it decays, physicists at Atlas confirmed that it interacts with both bosons and fermions, the particles that make up all matter. This finding further validated the Standard Model's prediction that elementary particles gain their mass through the Higgs field, which permeates the entire universe. The groundbreaking discovery of the Higgs boson was achieved by closely examining how it decayed into various particles, including photons, and the W and Z bosons. These decay patterns were crucial because they confirmed the occurrence of a process known as spontaneous electroweak symmetry breaking, a fundamental concept in the Higgs mechanism, which explains how particles gain mass in our universe. However, understanding the Higgs boson required more than just these observations. In the Standard Model, the Higgs boson interacts with two different kinds of particles, fermions and bosons, through specific couplings. Any unknown physics could potentially influence these interactions in ways we haven't yet discovered. The first clear evidence of the Higgs boson interacting with fermions came when scientists observed its decay into tau particles based on combined results from the ATLAS and CMS experiments at the end of Run 1. As Run 2 progressed with higher energy levels of 13 tera-electron-volts and a larger data set, researchers explored additional interactions. They detected the Higgs boson decaying into bottom quarks and being produced together with top quarks. More recently, the first measurements were made of the Higgs boson's interactions with second-generation fermions, such as charm quarks and muons. These findings have solidified our understanding of how the Higgs boson interacts with the matter particles that make up our universe. The discovery of the Higgs boson marked a pivotal moment in our understanding of particle physics, completing the framework of the Standard Model. After extensive research, this confirmation validated a fundamental theory about how particles gain mass. Contrary to what might be assumed, the Higgs boson itself doesn't directly grant mass to other particles. Instead, it represents a manifestation of the Higgs field, an all-pervading field in the universe. This field interacts with particles, giving them their mass. But why couldn't mass be simply assumed from the start? To answer this, we need to revisit earlier work in quantum field theory. Quantum fields are somewhat like the familiar electric or magnetic fields, but they also include states that we recognize as particles. These fields are categorized into matter fields, which include electrons and quarks, and force fields, which include photons and gluons. In the late 1940s, scientists successfully used quantum field theory to explain electromagnetic interactions involving photons and electrons. However, the theory struggled with nuclear interactions. The weak nuclear force, with its short range, implied that its associated particles must have mass, unlike the massless photon. Adding mass to these force-carrying particles directly led to problematic predictions that went to infinity. Physicists sought alternative methods to introduce mass into the theory. Peter Higgs, François Englert, and Robert Brout provided the solution. They proposed that an invisible field fills all of space and interacts with weak force particles to give them mass. This field is not zero even in empty space, breaking a fundamental symmetry in quantum field theory. Previous theories had suggested a massless, spinless particle, but experiments had ruled this out. Higgs, Englert, and Brout demonstrated how this particle could be absorbed by the weak force particles, resulting in these particles acquiring mass. The only remaining spinless particle was the Higgs boson. Another team of theorists reached a similar conclusion in the same year. Further studies showed that the Higgs mechanism could give mass not only to weak force particles but also to electrons, quarks, and other fundamental particles. The greater the interaction with the Higgs field, the more massive the particle becomes. However, it's crucial to note that the mass of composite particles like protons and atoms comes primarily from the energy that binds these particles together, not from the Higgs mechanism. Supersymmetry, unifying forces and matter. Supersymmetry, often abbreviated as SUSY, is a principle in theoretical physics that has garnered significant attention for its potential to explain some of the deepest mysteries of the universe. At its core, SUSY posits that the equations governing the fundamental forces of nature and the particles of matter should be treated as identical. This elegant concept suggests that for every known particle, there exists a superpartner with different spin properties, effectively doubling the number of particles in the universe. The standard model of particle physics, while immensely successful in describing a wide range of phenomena, is not without its limitations. It explains the interactions between fundamental particles and the forces of electromagnetism, the weak force, and the strong force. However, it leaves several critical questions unanswered, such as the nature of dark matter, the apparent weakness of gravity compared to other forces, and the origin of the Higgs boson. SUSY offers a potential framework to address these gaps. In the realm of physics, symmetry plays a pivotal role. Symmetry refers to a property where a system remains unchanged under certain transformations. For instance, a sphere appears the same regardless of how it is rotated. In the context of mathematical equations, symmetry implies that changing certain variables or components doesn't alter the overall outcome. The standard model itself is built on symmetries, but it distinguishes between the particles that carry forces, known as bosons, and the particles that make up matter, called fermions. SUSY seeks to unify these two categories by introducing superpartners for every fermion in the standard model. Supersymmetry predicts the existence of a corresponding boson for every fermion, and for every boson, a corresponding fermion. These superpartners are crucial to the symmetry that SUSY aims to establish. If matter and force particles are treated as interchangeable in the equations, the resulting theory would be more balanced and elegant. One of the primary motivations for considering SUSY is its potential to solve the hierarchy problem in physics. This problem revolves around the question of why gravity is so much weaker than the other fundamental forces. SUSY suggests that the existence of superpartners could naturally stabilize the mass of the Higgs boson, preventing it from being excessively large due to quantum corrections. This, in turn, could explain why gravity appears so weak compared to the other forces. Moreover, SUSY provides a compelling candidate for dark matter, a mysterious substance that makes up about 27% of the universe's mass-energy content but has never been directly observed. The lightest superpartner, often referred to as the neutralino, is a stable, electrically neutral particle that could account for the dark matter detected through its gravitational effects on galaxies. Despite its theoretical appeal, SUSY has yet to be confirmed experimentally. The Large Hadron Collider, LHC, at CERN has been at the forefront of the search for superpartners. However, no evidence of these particles has been found so far, leading some physicists to question whether SUSY is the correct path forward. Nonetheless, the principle remains a vibrant area of research, with ongoing efforts to refine the theory and explore its implications. SUSY represents a bold attempt to extend our understanding of the universe beyond the standard model. By proposing a symmetry between matter and forces, it offers solutions to some of the most perplexing problems in physics. Whether this principle accurately describes the universe remains an open question, but its potential to transform our understanding of the cosmos ensures that it will continue to be a focal point of theoretical and experimental research.